Alright, so in this next video we will introduce the idea of the inverse of a matrix, and then we'll go on in a couple of later videos to show how to actually compute this inverse using the methods that we developed in the last couple of videos for solving matrix equations. So before we talk about inverses of matrices, let's talk about inverses of numbers. So by inverse here, we mean inverse with respect to multiplication, right? So we know that we know two things about real numbers. First of all, we know that there's this distinguished element, right? So 1, the real number 1, is the so-called I'm not going to fit that in. It's the so-called multiplicative identity, right? In the sense that when you multiply by 1, right, the result that you get by multiplying by 1 is identical to what you started with, right? Now, we also know that for any non-zero number, you can compute the reciprocal, right? And the reciprocal has the property that if you multiply any real number by its reciprocal, any non-zero real number by its reciprocal, you get 1. You get this identity, right? And this plays a major role in equation solving, whether you kind of think about it or not. Because if I had a simple equation like let's say a times x equals b, where a is not equal to 0, well, the first thing I would do is I multiply both sides by 1 over a. 1 over a times ax is 1 over a times b. Then, on the left-hand side, I can kind of regroup using associativity. This is 1 over a times x. On the right, well, we just use the definition for, we can write that as b over a. We know that's how division is defined. And so then this, 1 over a times a, as noted above, this is 1 times x. And since 1 is the identity, 1 times x is just x, and we get that x is equal to b over a, right? So when you're solving an equation, right, we just say, oh, you divide both sides by a, right? But dividing by a means multiplying by the reciprocal of a, and the reason that you can cancel that a is that when you multiply by the reciprocal, right, any non-zero real number and its reciprocal combine to give you this identity element, which has this property that multiplying by the identity does nothing. So we want to basically recreate this with matrices. We like to say, okay, if I had a matrix equation, right, if I had a matrix equation, say a times x is equal to b, I'd like to be able to solve, if possible, for x, right? We saw last time there's an algorithm for doing this in certain cases, and the algorithm that we wrote down really only works if a is square. So if a is square, we can think about solving this equation. Even if a is not square, there might be methods for solving in the case when a is not a square matrix, but it's trickier, right? You have to kind of deal with one column at a time and analyze things on a case-by-case basis, and so I think we'll kind of, it's not something that we need to do, so we'll avoid that discussion. Okay, so here's how you define the matrix inverse, right? We know that among all matrices, this identity IN, right? Just to remind you that the identity matrix has the property that x times the identity is equal to the identity times x equals x for any n by n matrix x, right? Even if x is not square, this is still true. I just need identity matrices of different sizes depending on whether I'm multiplying on the left or on the right, because we need to make sure that the sizes match up for that product to be defined. So we say that our matrix A is invertible if there's another matrix B, so that multiplying A and B together gives you the identity. When this happens, we would say that that matrix B that does the job so that A times B gives you the identity, this guy is called the inverse. Now, we have to address this later on. Notice the use of the word the here in inverse. If a matrix does have an inverse, it only has one. You never get more than one inverse for a given matrix. The inverse is unique. We'll prove that later on in another video. So if I wanted to demonstrate to you for certain that these two, that this A inverse here is the inverse of A, right? How do I show that that these guys are inverses of each other? Well, I compute A times A inverse, right? So 2, 1, 3, 2 times 2 minus 1 minus 3, 2. And I do the first row times the first column. 2 times 2 is 4, minus 3. 4 minus 3 gives me 1. First row, second column, 2 times minus 1, that's minus 2 plus 2, I get 0. Then 6 minus 6 gives me 0 when I do row 2, column 1. And then minus 3 plus 4, I get 1. So I do get the identity. Now technically we should also check. We'll see later on that this is not necessary. If it works in one order, it's guaranteed to work in the other order as well. But that's not a fact that we have established yet. So really we should probably do it this way as well. Okay, so we do 2 times 2 is 4, minus 3, we get our 1, and again 2 minus 2, 0, minus 6 plus 6, 0, and then finally minus 3 plus 4, we do get a 1. So it works in either order, and so that tells us that these two matrices are indeed invertible and they are inverses of each other. Okay. Oh, I don't know why that's so blurry. Let me try again. Oh, that's kind of sad. All right. Sorry about I don't know why this did not render properly. My software is having some, I don't know, sadness. Okay. This, oh geez, even here, what is going on? Okay. Bizarre. We haven't had that technical issue before. Let me see if I can rescue this, guys. Right. And where are we? Here. Okay. Huh. Okay, I don't know what happened last time. We're back in business. Sorry about that minor delay. Alright, so not all matrices are invertible, right? Now, as with real numbers, we know that 0 doesn't have a reciprocal, right? And the same is true for the 0 matrix, right? I can't invert the 0 matrix because A times B will, 0 times B, right? 0b equals 0 no matter what b is. So there's no way for 0 to have an inverse because I can't get it to equal the identity. But even for non-zero matrices, and here's where things start to differ, right? With the real numbers, any non-zero real number has an inverse. For matrices, not all non-zero matrices have an inverse, right? So look at this guy here, right? 1 minus 2 minus 2, 4. I claim that this doesn't have an inverse. So A doesn't have an inverse. There are a few ways to see that it doesn't have an inverse, but one thing to note is that if I do A times the vector 2, 1, okay, if I do A times 2, 1, what would I get? I would get, I get 0. Okay, so there's something in the, there's a non-zero element of the null space here. Okay, and so if A had an inverse, right? If A A inverse exists, then it would be true that if I multiply both sides by A inverse times A times 2, 1 would be equal to A inverse times 0, 0, right? But on the left, I could write this as A inverse times A times 2, 1 equals, well, anything times 0 is going to give me 0. But this would be the identity matrix, right? By definition, this is supposed to be the identity matrix. Multiplying by the identity just gives me whatever I started with. And well, there's a big problem, right? The vector 2, 1 is not equal to the vector 0, 0, right? And so A can't possibly have an inverse, because if it did have an inverse, I run into this contradiction. So even if the matrix is not equal to 0, that's no guarantee that it has an inverse. We'll see later on that basically the condition is going to be that the rank of A has to be maximum, right? I have to get a leading 1 in each column when I reduce this guy. And so we'll introduce an algorithm for computing the inverse in the next video, and we'll see that that this is just the condition that we need. We need the reduced row echelon form of this matrix to be the identity in order for it to be invertible. We'll explore that in the next video.